cardinality of sets, which is the second part of the lecture. About Cantor's theory of cardinality. So this is the most of the stuff. So definition. Yeah, I remember that. Two sets A and B have the same cardinality if there exists a bijective function, which will denote B, a bijective function. So we just write like this is Bi, such that F A to B. So sets A and B. So there's a bijective function F A to B, which basically means which is basically like pairing each other to a set. Except this is a function only. It's gonna be a bijective function. Everything is mapped on to a different value. So this is bijective, and this is onto the same cardinality because they have the same amount of elements. Basically, in the course, it's actually kind of like elements only. It's kind of just think of the cardinality as elements. So notation. What the? Okay, that guy was speeding. If A and B have the same cardinality, you write. Now don't think of this as absolute value. It's not absolute value of a set. It's basically like taking amount of elements. So the same cardinality is the same amount of elements technically, yeah. Okay. If the cardinality of A equals the amount of elements in it, or for example 1, 2, 3, if it's like this, if this is A, then the cardinality of A is n, because there are n elements. A is finite in this situation. A is finite. N is a finite number. If there exists an injective function F A to B, then in this situation it's bijective or injective, so it's greater than or equal to. So basically in this situation B has more elements than A. You can think of it like that. But really there's an injective function A to B. That's what they actually mean. There exists an injective function F A to B. And now this is the same kind of principle, except if there exists an injective function A to B, and the injective function is not bijective, or this is not equal to this. Oh, sorry, B. It's always going to be equal. Then A is always injective, strictly injective to B. That's actually not a term. Strictly injective is not a term, okay? I just made it up. But, so, this kind of makes sense. If this and this is less than, okay, and they're not equal, then what else can they be? Less than only. Just think of it as elements, because then it makes arithmetic sense. Now, this is the theorem, Schroeder-Bernstein, whatever theorem. It's a theorem. Now, this is actually transitivity in its finest. So you should really think of for more intuitiveness, it's elements. But you shouldn't really think of these as elements, but this is just intuitive. Because if you think intuitively, then this obviously makes complete sense. Because remember the same thing with sets. Couple days, like last lecture. Like if A is part of B, B is part of A equals to B. Same situation here. A is less than or equal to B. So if there's an injective function A to B and an injective function B to A, then A equals to B, so it's bijective actually. So the function is actually bijective, not just injective. Which explains why there can't be an inverse function B to A. That just can't exist. Unless it's for bijective functions, because it's equal anyway. Definition. It talks about infinities a bit. Okay. So, if the cardinality of A equals to the cardinality of the natural numbers, then A is countably infinite. So this is countably infinite. Oh yeah, we're going to get some very interesting theorems after this. But this is countably infinite, okay? Like if they have the same amount of elements. There are many other sets which have the same amount of elements, and by many I mean a couple. So, or if A is finite, or if this is finite or countably infinite, then it's countable. Otherwise, it's uncountable. Like this thing over here, but actually, is that countable? Actually, no, it says countable, right? Wait, but like this thing right now. Okay, is that even true? Let me check. So, theorem. This is gonna be theorem 1. The set of even numbers. So when I say the set of even numbers, I'm going to have to write a formal notation. So it's basically 2n, all n natural numbers. If this set, the even number set, equals to the natural numbers. Now I'm going to denote this to make life simpler for me, like we did for the irrational numbers, we're going to do it for this as well. And for the upcoming odd numbers, we'll do this. So, till, and by the way, these, again, not formal, not true, let's make it not true. Okay, so this is just our theorems that the amount of elements in the even number set is the same as the natural number set, because you can pair them off. Actually, this is not even part of our proof yet, but actually this is a part of our proof, but here's a sneak peek. We can pair them off. And since an infinity really does break intuition, it breaks all intuition. And anyway, this is countably infinite. Nice to know. 2. The set of odd numbers, which I'm going to do this because I'm too lazy, equals to the set of natural numbers. Again, if you see this as a thumbnail, see it says real, not actual. It's not actually written by that. Okay? So first we want to show that n equals to Give me a second. Someone is knocking. So, oh, no one's knocking. Okay, so no one's knocking. So let's continue. I know. Oh my god, work upstairs. I live in an apartment in the middle of the city. Yeah. Okay. So we want to show this. Let function n 2e we choose this function is 2n. N is an n. We first show f is 1 to 1. So i.e. if fn1 equals to fn2, then n1 equals to n2. So fn1 equals to fn2. So 2n1 equals to 2n2. And using the algebra, we have to deduce n1 equals to n2. Now we want to show f is surjective. So and by the way, the odd thing is going to be they made it a homework problem, and I don't really have the details for that. Yeah. I should really start checking the homework thing so I can start bringing these proofs. Because right now all I have is notes. I haven't even expanded my notes from the first time. There exists an n such that fn equals to n. So let m be in the even numbers. Then there exists an n such that n natural numbers such that m equals to 2n. Then fn equals to 2m equals to m. So fn equals to m. Thus f is surjective. Nice to know. Now I'm gonna give you how many theorems? 3 theorems, which one of them I didn't even 3 theorems with no exact proof of them. Sorry for all the proof wanting people, but this one's actually a homework problem, so if you want to look at look at problem set 2 of 18100A real analysis MIT OCW.edu. But so basically the integers are the amount of elements in the integers have the same amount of elements in the natural numbers, and it's because we can pair them off. Like, they actually gave the basis for this, but I didn't write that down because it's a bit weird. They do it a bit weird, but like it can be paired off in a very weird way, but still paired off. Oh yeah, I think I remember now. So the even numbers pair, since the even numbers and the natural numbers have the same size. I think this might actually be an okay proof. Like, this is good enough. Here's some details. -2, -3, -4. So this pairs up to -2. 2 pairs up to -1. So basically, all the even numbers pair up to the negative numbers. 6 paired up to -3. And it's possible. It's possible. 7 and 8. 8 pairs up to -4. And then 9 and 10. And all the odd numbers pair up to the well, actually, this is also a part of the integers. Well, oh yeah, 0. What happens with 0? Oh shoot, what happens with 0? Okay, so what happens with 0 though? Is 0? Okay, so let's not think about that right now, cause is 0 an integer? Yeah, 0 is an integer. Is 0 an integer? I can't believe I'm even typing this. Is 0 a natural number? So no, that's kind of weird, but we'll think about that, okay? But you guys can think about that. I don't. But and same thing can happen here. The odd numbers can just match up. Oh shoot. So okay, this is very messy. So basically, if n is an even, then n matches up to n divided negative n divided by 2, and it's possible. And yeah, I'm going a bit up. I was not supposed to say this. I was just supposed to say the theorem, but n is an odd. Well, n goes to n divided by 2 plus 0.5 m, or it's m plus 1 divided by 2, because 1 goes to 1, 3 goes to 2, and it's possible because it pairs off. The odd numbers pair off to the real numbers. That's the properties. That's probably why they asked this homework problem. I still am confused about the 0, but there's probably something there. But yep, this works. We gave a basic idea. So now, theorem. This is the positive rationals. So I'm just gonna, I could denote this by Q over 0, or I have to torture myself and do this. This is a theorem. So positive rationals So this is a theorem which we're not going to prove because I have no idea how to approach this. but it is hard to prove. So, that's the theorem, positive rationals, and we'll extend this theorem not just to positive rationals. What's the point of only positive rationals? Let's do all rationals. Yeah, let's do all rationals. So, same thing works for all rationals as expected. Even the 0, and that 0 really messes me up. Like, what is that 0 doing? Like, I'm just confused. Again, you should remember I'm 11 years old, so I'm still thinking of this stuff. But these are the two theorems. And now we have a question which is gonna guide us into the next part of things. It's kind of an important question, and people were wondering about this. Is there a set bigger? Does there exist a set whose cardinality is bigger than the natural numbers? Huh? Because natural numbers is only like countable infinity. I mean, I think the real numbers is bigger. Is it? I'm not sure if the real numbers is bigger, but oh yeah, there's another question which is very interesting. So, by answer, we'll define something. So, if A is a set, then the power set of A equals to, so the power set, no, that was not good. Okay, I can't do this one. Basically a P with a curve, like, I'm just gonna draw like this. For some reason, something like this, I don't know, in my notes. Like, this just doesn't look good. Power set A equals to elements B, we'll call the elements B, where B is a subset of A. So basically, it's all the subsets. It is all the subsets of A. That's a lot, not just A itself. That's one set. There's going to be another set with just a part of it. There's even going to be the empty set and just many subsets. So basically, the cool thing about this is that you think, so wait, the rational number, the empty set is obviously not a part of the empty set. Here, the empty set, oh yeah, the empty set is a subset. Cool thing is, the empty set's actually a subset, the complement of the empty set. Like, you just think that's impossible. But no, it isn't. It's a subset. Because there's nothing in it. I was just thinking, yeah. So, examples, A equals to none. The power set is the same thing, so I'm not even going to write that. This is P of A. I'll only do this example 1. So it's just null. One. And for 1 and 2, that's 4 outcomes, which I really don't want to write. But it's the null, it's 1, 2, and the set 1 and 2. So, theorem. I don't even have to say this. If A is a set, because at this point, context, then the cardinality of power set of A equals to 2 to the cardinality of A. Like in the previous example, there were 4 things, 1 and 2. So there was null, 1, 1, which is 2, 2, which is 3, and 1 and 2, which is the 4th one. So there are already 4, which is pretty nice. And 2 to the 2, which was the amount of elements in 1 and 2, is 4. So, oh yeah, here's another theorem, which is basically the one which answers our question. Cantor. Of course, this is related to Cantor. Cantor's theorem. Cantor. Okay. So, if A is a set, then A, the cardinality of A, is less than the cardinality of the power set of A. Always. For any set. Any set. Wait. You sure about that? Oh, yeah. Because the cardinality of the empty set is 0. And the empty set, it's 1. Power set of empty set is 1. 2 to 0 is 1. Okay. So, theorem. This is actually kind of a remark. Oh, yeah, I was looking at something. Sorry. Oh my god, I take long pauses. Here, cardinality of the natural numbers is officially less than something. The power set of the natural numbers. Which is less than the power set of the power set of the natural numbers. And yeah, the small remark at the bottom, I don't understand that. And now we're like, okay, this is pretty boring. The power set of the natural numbers is still related to the natural numbers somehow. We just defined something. So I have a question. Does there exist a set such that the cardinality of the natural numbers is less than A, which is less than the power set of the natural numbers? Answer this question for me. Well, sad to say, sad to break your heart, we don't know. We just don't know. It is called the Continuum hypothesis. Actually, we know. Do we know? So I'm just gonna... I actually just said it's way out of the scope of the class, but let's see. Let's see if we can make your minds happy. To Continuum hypothesis. Every infinite set of real numbers is either the size of natural numbers or the size of the real numbers. What? So we need infinite cardinals, so Aleph. We get Aleph. Aleph null. Aleph 0. So that's the size of the natural numbers. The set of the... That's... Oh yeah, I should probably write this because this is probably interesting stuff. So the cardinality of the natural numbers is defined as... Aleph null. So it's defined as... I actually saw this in a Vsauce video. Do you guys watch Vsauce? He's a nice guy. but it's about Aleph null. Okay, I've heard Aleph null. Wait, is there a better way to draw this? It doesn't look good at all. Aleph. Okay, so let's see if we can draw this. Okay, I like the simple version better. So, the cardinality of the natural number is equals to that looks like a guy who's that looks like something not too special. But oh yeah, it should be okay, whatever. However we draw Aleph null. That's exactly the set of the natural size of the set of the natural numbers. Aleph 1, Aleph 2, Aleph 3, Aleph 4. So let's just read what this thing has to say. I actually don't know this. Is learning. The next biggest cardinal number is Aleph 1, Aleph 2, Aleph 3. What's the cardinality set of the real numbers? Can't formulate one possible answer to this famous continuum hypothesis is what I just said. Every infinite set of real numbers is equal to the size of the natural numbers and the size of the real numbers. And the continuum hypothesis is equivalent to saying that the real numbers must have cardinality Aleph null. If the continuum hypothesis is false, it means that there's a set of real numbers that's bigger than the set of the natural numbers, but smaller than the set of real numbers that's bigger than the set of the natural numbers, but smaller than the set of the real numbers. In this case, the cardinality of the set of the real numbers means at least Aleph 2. The continuum hypothesis is true or false. The problem was so pressing that David Hilbert, the first of the list of 23 problems, finished in 1900. So, Kurt Gödel proved in 1938 that the continuum hypothesis is consistent with the axioms of set theory. Axioms, which is like adding the continuum into does not result in contradiction. This is far from proving the continuum hypothesis is true. Proof will describe how the truth of the follows from the axioms. Theory for the continuum hypothesis is so constructible universe. Contradiction. Okay. It took another 30 years to answer that question. Boltzmann proved in the 1960s that consistent with the axioms of set theory that continuum hypothesis false, results from which you receive the field metal. Cohen invented a new material, the forcing. Okay. Oh god. So there really is no answer. Oh god. That was a lot. That was way too deep. Okay. So that very deep thing, and it's way beyond the scope of real analysis. So if you didn't understand a word, because I barely understood it, it killed me. I left null. Really? I mean, like, it's kind of cool to know what people use to describe the real number. So, anyway, guess we're gonna end today's lecture 2. Yeah, it's the end of lecture 2, so bye, I guess.